All right, our next speaker and our last presentation for today before the poster session is John Power. You push this button and this is a laser.
Oh, wow.
Yeah, I know. Be careful.
I can use this too.
Okay.
No, I want to start off by thanking everyone for coming, especially people from outside of Alaska. And I also want to thank Madison and Benaz and Sky and the rest of the organizational committees, and particularly Sky for getting us into such a nice building. What I'm going to try and talk about today is a little bit of arc-wide geophysical insights for magmatic systems. I'm going to try and step a bit away from instrumentation and data sets and ask some bigger scientific questions, go a little bit out of my comfort zone, which feels a little uncomfortable giving a talk, especially to a group like this. And I notice already that my slides are slightly different than I had them on my screen, but that's okay. What I've organized, we're going to talk a little bit about instrumentation and opportunities and its scientific opportunities from the geophysical side that I'm going to try and concentrate on. Going to go a bit into transcrustal magmatic processes, which is a nice buzzword that we all, I think about. And then talk some about arc-wide tectonic controls on magmatic systems. Because it's a geophysical talk, I'm going to try and focus on these things. Because I'm a seismologist at heart, we're going to talk more about seismology and geodesy. And Terry and Connor have talked about some of these other developing techniques, which is great. The other thing I wanted to do was offer thanks to a lot of people in this room, because a lot of what I'm going to talk about come from conversations that I've had with many of you over the past many years. I've tried to reference things appropriately, and I'm going to apologize now for the ones that I've forgotten or missed, because there certainly are those. This is a slide that Madison has already showed. It's why we're here. There's a lot of diversity and magmatic systems throughout the Aleutians that I think show a lot of promise for future research. One of the things that's very exciting about Alaska is if you're going to understand explosive volcanism in the United States, you're going to work here. I like to slap people in the Cascades around a bit. Right. This is a map showing the AVO seismic networks that Max Enders went over earlier. The dates are when AVO first instrumented the volcanoes. You can see that when AVO started, we were working mostly from Spur, basically down to Katmai in 1995. In the mid-90s, we began a very aggressive program, and the intent was to monitor or instrument all the volcanoes in the Aleutians. This is something Steve McNutt will remember. To address aircraft safety, we began moving out. We, of course, never quite achieved the objective of instrumenting every single volcano, but the dates here are when instrumentation went in on the individual centers. There's a lot I want to say about this slide. Some of the volcanoes actually were instrumented before AVO was founded in 1988, and those, I think, represent some special opportunities. Certainly the volcanoes around Cook Inlet, Spur, Redoubt, Augustine were instrumented prior to that. These volcanoes in some ways are very special, along with Pavlov and a lot of the work that Steve McNutt did. These are volcanoes where we've made geophysical observations through one or even several eruptive cycles, which I think is very important for research. And I think it provides a special opportunity in terms of designing new studies or investigations. Certainly, other volcanoes fall into that category as well. The Katmai cluster, Shishaldin and Okmok are rapidly moving into that category. And all the other volcanoes, Great Sitkin experiencing a now almost 4-year-long eruption, and other volcanoes coming along, a lot of similar to what Matt was just talking about, of where we have well-developed studies and background information. There also are, of course, places where we have relatively short periods of time of instrumentation and where very little work has been done. And there certainly are those frontier volcanoes where no instrumentation currently exists. We almost never talk about Nazca or Amukta, which are also exciting in their own way. Seaguam, although I know you've been to Seaguam, Terry. This is a plot, which is a little bit fuzzy, at least for me, that shows the AVO earthquake catalog. We've tried to catalog earthquake activity from 1989 through 2000. This shows through 2018. My slide here is a little bit messed up. We now have here about 170,000 reviewed earthquake hypocenters. This data is available for download from this USGS report, and since 2019 is available through the USGS comprehensive catalog. That includes locations, magnitudes, and those kinds of things. Most of the data is, or the continuous data now, thanks to Jenny Nakai, goes back, I think, till the mid-1990s. It's available at Earthscope. We've seen this before as well. The one thing I want to point out here is that sort of two things. One is the AVO seismic network and instrumentation, which goes well beyond seismicity, is constantly evolving and advancing. And that presents also a challenge or opportunity. If you look back through the eruptive cycle, at say readout in 1989, there were 5 short period instruments. There now is a robust network there that includes a lot of instrumentation, the things that AVERT has done, places like Cleveland and Ockmont. There is kind of a moving target when you try and look at the processes that are happening in Alaska volcanoes, which at some volcanoes proceed over a decadal time scale, but the time scale in considering how to study these processes is important. Decades, centuries, thousands or tens of thousands of years at some of these volcanoes. So I want to move now and talk about transcrustal processes and how we observe that at AVO. I'm going to start at the base of the crust in the uppermost mantle, a place where I've tried to be very involved in research. Something that's developed over the last really 20, 25 years is looking at deeper seismicity. These are deep, long period events. I've got waveforms here that show various examples of events that we see. This plot here was put together by Dane Kettner. This goes along the arc. This is spur over to Little Sitkin. I'm sorry, this is kind of blurry. It wasn't that way when I made the slides. And what you see, and it's interesting, is we do see deep, long period events, volcano-tectonic earthquakes in the uppermost mantle and the lower crust. And this is something that has happened, or we've observed these at every volcano we've looked at, if we've looked at it long enough throughout the Aleutian Arc. A whole bunch of interesting studies have come forward with this. We're now able to link it to the movement of magma and volatiles in the lower and mid crust. A sort of exciting recent development is the work that got started at CIDER by Kathleen McKee. And she has a very nice poster here that tries to look at arc-wide, deep, long period earthquakes and relate it to things like melt inclusions and related geologic knowledge. We'll go to the next slide. There are some very exciting, talking about transcrustal processes, some very exciting places where we have been able to see activity in the upper mantle, lower crust that relates to surficial activity. Some of the best examples are Spur, where this has happened multiple times, Readout, Katmai, Shishaldin, Akatan, and Great Sitkin. This is my favorite example. This is a time depth plot. This is hypercentral depth from the top of Readout down to about 40 kilometers depth. The red bars here are when Readout was erupting. The data goes from 1989 through 2009. The black dots are earthquake hypocenters, and the red symbols are these deep, long period events. In this case, we see strong evidence that this activity in the lower crust, upper mantle, was actually a precursor to the 2009 eruption. Interestingly, people like Ronnie and Cindy Werner identified prior to the onset of deep seismicity deep geodetic unrest and increased CO2 coming out of the volcano. Of course, my specific interest in this was trying to extend the forecasting window to an earlier period of time. That's a little bit questionable. But to me, this is a very exciting and interesting data set at readout. And I know Banaz has been cranking through this, wherever there she is, through this in recent years, looking at melt inclusion data as well. This is a more recent example of the movement of magma through the crust. This is from Great Sitkin. This is a 3-day-long helicorder record. What I've marked here are located deep long period events with the red arrows. This happened on July 30th, 2016. About a day later, after we first noticed these deeper long period events, we began to see shallow long period events in the upper crust. This is an epicenter map and east-west cross section. The very exciting thing here is there was this evidence for a linkage at Great Sitkin between the mid-crust in this case and the shallow depth. Depending upon how you calculate the beginning and ending of these episodes, it suggests a movement through the crust at something like 100 to 700 meters per hour, which seems to me incredibly fast. And we've argued about whether this was the movement of volatiles or a pressure transient. Diana's nodding because we've argued about this a lot. This is very similar to what people have reported for migration rates at Pinatubo and Kluchevskoy. This is right now, I think, one of the nicer Aleutian examples of how fast things may move through the crust, whatever it is. And this is a research opportunity.
Documented meters a second.
Well, you could do that too. When we move into the shallow crust, magma is easier to find. There are a whole lot of great studies, and I think really an explosion of work if you look over the last 30, 40 years in the Aleutians. I won't go through all of these, obviously, but it is a very exciting thing. All these different techniques coming to bear on looking at activity in the upper crust. However, there's still a long way to go. I feel if you look at what's happening right now at Spur, we are struggling to understand exactly where the magma is and how it's behaving. But I also, want to encourage people who are involved in all these kinds of studies to continue. I want to move now and talk about the arc as a whole and what we see moving across the arc. This, of course, is a plot that I made a number of years ago when we were talking about the island of 4 mountains. And again, I'm sorry that this is a little bit messed up. What we've shown here, obviously, is the arc, the convergence vector, something that Jeff Freimuller, Ronnie, and others have worked on here. This is the plate motion and the rates in centimeters per year and the convergence direction. What I plotted here is the size of calderas based on the size of the circles corresponds to the caldera area in square kilometers. And we see this is Emmons caldera and Okmok. I'm annoyed by this. And what we see and what studies show is that where we'd expect large calderas to form and where we would be able to store magma in the upper crust for thousands to hundreds of thousands of years is where plate convergence is rapid and normal to the subducting plate, which is exactly what you see in the Aleutians here. This follows along by studies by Hughes and Mahood and Sheldrake, which is a more recent study, dropped off the bottom there. The other thing that I think happens here that I'll come back to in a minute is we don't see large calderas forming either in the Cook Inlet region or in the Andreeff Islands. And that's because, as predicted by these earlier studies, you're getting into areas where there is a more oblique subduction. Magma tends not to stall in the crust, but come through as little blips. I felt that in talking about the Aleutian Arc and the volcanoes, we would be remiss if we didn't talk about the great earthquakes. So I put this slide in. This is somewhat out of my depth. This shows all the magnitude 7s in the Aleutians and larger from 1900 to 2023. This is from Wood et al. 2023. One of the questions that we've long struggled with, and we're often asked by the public, is if we have a large earthquake, are we going to see volcanic eruptions? The answer, I think, that is currently best is sometimes if the volcano is pre-primed. This plot shows cumulative moment from 1900 through 2020. And this is, again, this point. This is the period of AVO instrumentation, which is very short compared to what we see. Oh, 3 minutes remain. I'm gonna have to hurry up. There are also a number of ways that these earthquakes impact the volcanic systems. Stephanie Prejean and Dave Hill did a very comprehensive study published in 2018 looking at dynamic triggering. They found, a number of volcanoes that are more susceptible to triggering. I'd encourage folks interested in that to read that paper. There are certainly more research topics there. The earthquake that is actually the one that has happened since we had instrumentation in is this magnitude 8.2 on July 28th, 2021. We've looked at how this may have affected the different volcanic systems. Ronnie Grappenthin has looked very hard at how this might have impacted Aniakchak, where we had episodes first of deep long period events and then increased shallow seismicity and then uplifts starting in 2022. In the interest of time, I'll go on. I want to talk about triggering at Tanaga. This is a place where Jackie Kaplan-Auerbach and students have been very active. Here's our magnitude 8.2. This was immediately followed, or very shortly followed, in August and September by a swarm of deep, long period earthquakes that we had never seen since monitoring began at Tanaga in 2005. This is somewhat questionable. The epicentral distance from Tanaga is about 1,400 kilometers. Again, an evolving research topic if someone is interested. What I want to talk about last is triggering and the oblique subduction zone. And again, now I'm going to focus on the Andreev Islands. This is where subduction actually begins to be inclined over here like this. What happens in this situation is the strain partitioning begins to break the plate, and we set up a series of bookshelf faults. This was first identified by Geist in 1986. Rupert et al. Went further and identified a number of faults between the various volcanoes in this part of the arc: Korovin, Great Sitkin, Tanaga, Gorella, Semi-Sapochnoi. Moving fast for Madison. This is, I think, my last slide. This is work that was done by Kevin Lawley and Jackie Kaplan-Auerbach. This is Tanaga. What we see here is a number of these bookshelf faults that were, I believe, first termed bookshelf faults by people like Pete LaFemina. These are left lateral strike slip faults that occur along the volcanic arc, which is the weakest part of the arc that begins to fracture based on that subduction zone angle. There is evidence that these faults communicate with one another. This is data from Great Sitkin on this side. Here we had two magnitude 4.2s in 2002. This is a time longitude plot or space-time plot. What you see is that the first fault was here. It then triggered an earthquake over on the other side of Great Sitkin. The exciting thing that happens here is, and that comes out in this plot as well as what happened in Tanaga in 2005, 2018, where Craig Gabrielson is currently working, as is Ronnie and students. There is, I think, here evidence that the volcanoes activate the faults. The faults also show evidence of activating the volcanoes. So less than a great earthquake, but still this very interesting interaction between tectonic faults and the volcanoes. This has been studied fairly in a bit more detail in Nicaragua by Higgins et al. And recently published, where they did a lot of detailed modeling. I think there's a great opportunity here in the Andreevs to do some of that work as well. Sorry, I've gone over time.
Great. Any questions for John? Yeah.
Uh-oh.
That was quick.
It's good. So I'm just curious, so these DLPs, do you know if they're in the crust or in the mantle, or have you been able to tell?
I would say that they occur in both. And this was when we first started looking at these, and it was really Randy White at Pinatubo. He was kind of brought this, I think, into the awareness of the US community. Folks in Japan had been talking about it a little bit earlier than that. And some of Kathleen's poster has, very nice plots of where the earthquakes locate and what we know about the crust mantle boundary, which I think is an area where you've done a lot of research. But I believe that they occur across that boundary. There is some evidence that there is a bit of structural control there. And I think Kathleen's poster has the best, the most comprehensive diagrams that show that, but it would be good to get your input on exactly where the crust mantle boundary is in some of these parts of the arc, because it does vary, as you know. Steve.
Did the ability to see the default events increase a lot when you switched over to broadband instruments?
It did. And I think really the thing that actually helped the most was S-wave identification. And you and I remember talked about this long time ago, whether these were actually S-waves or not. And I think that the broadband, the upgrade to broadband certainly helped with that a great deal. And I think we do see more recently because of the horizontal instruments. Connor.
Any of the spikes in the seismicity through time were associated with a specific earthquake, apart from the 1996 anomaly. What was that?
And again, I'll point back at Steve, because Steve was the one. In 1996, in the fall, we began to see a great deal more earthquakes throughout the arc than we had seen in prior years. And it was very unusual, we felt. We had no good explanation for it. Steve actually went ahead and wrote a paper about this, which we call the 1996 anomaly. There was activity throughout at least the eastern half of the arc, which was kind of unprecedented. I would say now that we see, 2003, where we saw heightened activity in Katmai, Tanaga, where else do we see increased? There are other episodes like this where you begin to wonder what happened. Steve, probably during the break, catch Steve, because I think he's the expert on what happened in 96.
It's all the instruments.
On that same graph, when we talk about the numbers of events, there are, speaking of a couple of volcanoes, that have tons of seismicity that's non-located, right? So Garaloy, Shishaldin for a long time. So I'm wondering for a lot of that, when you talk about the numbers of quakes, whether you have a sense for how your magnitude threshold vary, your detection threshold, whether there are also comparable things that are just counts and not locations.
It's a very good question, Jackie. And this is something we've discussed at AVO in recent months, particularly with unrest at Spur. And I think speaks immediately to a limitation of our earthquake catalog. There are tears in the data of all types. And if you look through history, the 40-year now history of AVO's earthquake catalog, when we started off with short period vertical instruments only, now moving improved computer systems, improved detection algorithms, improved instrumentation, we begin to see more. So there certainly is that effect. There also is now much greater ability, because we now are able to record the data continuously and deposit it at the EarthScope DMC. If you start doing template matching, you'll find thousands more. I've shown plots of deep long period earthquakes. There are folks who are out there template matching increasing the catalog by orders of magnitude. Yeah, Connor. It's a great thing, and you know, looking at the tears in the catalog as they occur, and this is something that happens in all earthquake catalogs, I think, is as these changes have occurred and our ability to process data has improved, changing people who are actually determining the PNS phases, that puts tears in the catalog. There are magnitude differences. We've gone back and tried to correct those. Some of them we can't correct.